Hi, I'm Samantha. Today I'm going to introduce you to my research on recyclable superhydrophobic anti-moisture activated carbon pellets for air and water purification. Activated carbon is a commonly used low-cost adsorbent. It's used to absorb pollutants from sewage and it's used to remove oils, dyes, and volatile organic compounds or VOCs from water and air. However, it has limited absorption performance in high humidity conditions due to its high affinity to moisture, which makes it very ineffective. That is why we're searching for superhydrophobic activated carbon. SAC or anti-moisture activated carbon has the potential for the development of efficient and environmentally friendly methods for air and water purification compared to conventional activated carbon. Moving on to the method, so the first thing that was done was superhydrophobic silica nanoparticle solutions were synthesized, and then this solution was added to the activated carbon to make it superhydrophobic in nature, and hence resulting in SAEC. Now I'm going to compare SAEC with AC. So the first thing I would like to mention is the moisture resistance. SAC has improved moisture resistance compared to conventional activated carbon. As you can see in the graph in figure 1, the plot of AC has a much higher weight increment than that of SAC because SAC didn't absorb moisture, it was able to absorb pollutants, that's why. Whereas yeah, AC had a much higher weight increment because it had absorbed a higher mass of the moisture, which makes it higher in weight, and hence it was not able to absorb much pollutants. The second thing I would like to talk about is air permeability and moisture purification. As you can see in figure 2, there's a setup shown in which vapor passes from one end to the other, and either an activated carbon or an SiC slit is placed in the center, and the difference in relative humidity is measured between the two slits. And you can see in the plot that the SAC did not have much difference in relative humidity, whereas AC had a very high difference in relative humidity. As I mentioned before, that is due to the moisture content that it absorbed, the AC. And thirdly, there's the SAC has improved absorption of dyes. As you can see in the figure in the third image, in the first image, sorry, that the first both the set of dye solutions are that of methionine to aqueous solutions, but in the first one there's AC immersed, and in the second one there's SAC. As you can see, SAC was able to completely absorb all of the dye from this aqueous solution, whereas AC was not as competitive and barely able to absorb any of the dye from the solution. That's why there's very any color fading. And you can see that in the graph in figure 3, where the removal efficiency of the dye of SAC is much better and sustained compared to AC. And AC also has a much higher weight increment once again compared to SAC due to the moisture affinity. The next point I would like to talk about is improved absorption of SAC of oils from macroemulsions and volatile organic compounds from water. As you can see in the image, in the first image, AC is not able to remove any of the VOCs or volatile organic compounds from the water, whereas SAC was able to completely absorb all of the VOCs from the water. Once again, due to the moisture affinity difference. And in the C image, you can see that AC was not able to remove much of the oils from the macroemulsions, whereas SAC was able to completely remove and absorb all of the oil from the macroemulsions because it's a better absorber of oils from macroemulsions as well as volatile organic compounds from water and air. The final point that I would like to compare is the improved recyclability of SAC compared to conventional activated carbon. As you can see in figure 5, uh, you can see that the weight increment in the absorption cycle of AC is much higher, and it is also having a much lower desorption of the vapor, and it's not able to completely desorb the vapor, whereas SAC has a much lower weight increment as well as it was able to completely dissolve out of the vapor in a much shorter period of time. It is also true that, as I mentioned in the image that you see, that SAC has a much higher recyclability efficiency than conventional activated carbon is, and the recycling SAC is also very good at um, all these absorption of pollutants. So moving on to the conclusions. In my conclusion, superhydrophobic anti-moisture activated carbon or SAC is an excellent solution for iron water purification, and it is a great solution for the limitations of conventional activated carbon due to its high affinity to moisture. SAC has superior water vapor permeation performance as well as improved absorption capacities for dyes, oils, and VOCs. There's volatile organic compounds. And finally, it also has excellent recyclability compared to conventional activated carbon, making it a more environmentally friendly option for air and water purification. For future work, I would investigate the potential of SAC for large scale wastewater management, as well as the purification and the removal of pollutants from industrial wastewater, as well as factory emissions of air, factory emissions, that is. And it would also be very nice and interesting to compare its effectiveness with other hydrophobic adsorbents. And finally, it would also be very nice and interesting to compare and combine SAC with other adsorbents to make it to improve its performance. These are my references. I thank the chemistry department and Dr. Class Kelleher from SUNY Binghamton for allowing me and giving me the chance to present this to you. I thank you and I welcome any questions you may have. Thanks.